Physical light travels as chaotic, expanding waves, but to understand its interactions, we must strip away complexity and track it along single, clean paths. We call this abstraction the ray model of light. By treating a light beam as a perfectly straight geometric line, we can use basic math to predict exactly where it will travel. When one of these light rays strikes a flat, smooth boundary, it bounces. This behavior is governed by a strict geometric axiom known as the law of reflection. This diagram shows the rule. The incoming incident ray angle perfectly equals the outgoing reflected ray angle. We measure these against the normal, an imaginary perpendicular line drawn exactly where light hits the boundary. Compare these surfaces. On the rough wall, microscopic ridges scatter the normal lines, creating random diffuse reflection. On the smooth mirror, the normal lines are parallel. The rays bounce in perfect unison, requiring your eye to be precisely positioned. Because this specular reflection follows a strict, organized geometry, we can calculate exactly how smooth surfaces manipulate light to form images. You see this geometric calculation every time you look into a flat bathroom mirror. Here, light leaves the physical bottle, strikes the flat glass, and reflects into the eye. But the brain assumes light travels in a straight line. It extrapolates those rays backward, mapping an object that appears directly behind the glass. We call this a virtual image, an optical illusion created entirely by your visual processing. Because the angle of reflection equals the angle of incidence, the physical distance from the object to the mirror exactly matches the virtual image distance. The depth you see in a flat mirror is just symmetry at work. If a flat surface creates a perfectly symmetrical illusion, what happens when we bend the geometry? Curving the mirror shifts the angle of its normal lines. Parallel ways striking this surface are steered toward the center to intersect. This diagram plots that exact point of convergence, called the focal point. If you map the mirror as a complete circle, it has a center of curvature. By tracing the angles, the math reveals a strict rule. Focal length is half the radius. But there is a structural limit. This diagram reveals what happens if the mirror's curve is too steep. The geometry at the extreme edges fails to perfectly align with the center. The outer rays miss the sharp focal point, creating a smear known as spherical aberration. To reliably predict image formation and avoid a blurry mess, optical engineering relies on small, gentle curves where the focal point remains absolute. Once that precise focal point is established, we can use a method called ray tracing to map exactly how an image will form without relying on any math. Here is an object in front of a concave mirror, with its center of curvature and focal point mapped. To locate the reflection, we draw 3 lines. Ray 1 travels parallel to the axis, then reflects directly back through the focal point. Next, we map ray 2. This line drops through the focal point first. Because it is the exact geometric inverse of the first ray, it has to reflect parallel to the axis. Finally, ray 3 travels straight through the center of curvature. Striking the mirror at a perfect 90-degree angle, it reflects straight back. Tracking these 3 lines reveals they converge at a single coordinate, where the image forms. Notice the difference here. The light rays are physically intersecting in the real space in front of the mirror. This creates a real image, entirely different from the virtual illusion behind a bathroom mirror. And because that physical intersection happens below the central axis, the resulting image is projected upside down. By plotting just 3 predictable paths, we can define the exact location, orientation, and physical state of any reflected image. Ray tracing proves the mechanics visually. But to actually engineer optical devices, we have to translate those converging lines into rigid algebra. This is the magnification equation. It mathematically links the scale and position of the resulting image back to the original object. On the left, magnification is a simple ratio, the height of the final image divided by the height of the physical object. The right side introduces a critical rule of optics called the sign convention. Any distance on the reflective, front side of the mirror is recorded as a positive number. Anything trapped behind it is negative. Because a real image forms physically in front of the mirror, its distance is positive. Plug that into the equation and the built-in negative sign forces the final magnification to be negative, algebraically proving that the image is inverted. The math perfectly mirrors the geometry. The curve of the surface dictates the optical reality. These rules rely on light bouncing off an impenetrable wall. What happens to the geometry when light encounters a transparent boundary, like water or glass? Instead of reflecting, the light penetrates the surface and bends. This is refraction. It happens because the physical speed of the light wave drops when it hits a denser medium, forcing the geometric angle to snap. If mastering bouncing light gave us the architecture of mirrors, mastering bending light opens the next frontier, the invention of lenses, and the ability to build telescopes to observe the universe.